Second section of the chapter, differential equations with Laplace transforms. You got to be able to do this because what we're working toward is using this discontinuity idea to do explosions, which is the coolest thing. I mean, just the coolest thing to be able to mathematically model explosions. And the book, what a great choice. Out of all the things to motivate Laplace transforms, why not explosions? So we're heading toward that. It's not very far away, but we need to be able to handle a discontinuity. So we study the simplest discontinuity on the face of the earth, this guy called u sub 4 or u sub a. It's called the Heaviside function. And it's a very simple function. It's either 0 or 1. And it's 0 all its life until you hit t equals, in this case, 4. That's a subscript 4. So at 4, the function is now worth 1. A very boring function, not very strange, but we can handle it in a differential equation. And you can see where this is going because the next thing will be, can we handle it when u sub 4 is times another function? Well, it's actually easy because the u sub 4 is worth 0 until it comes on, and then it's worth 1. So it's really like having the ability to have another function in a forcing term, and you just turn it on when you need it. It's very cool. All right, so to be able to do this, we have a very simple differential equation, first order, dy dt equals negative 2y plus u sub 4t. Not much different from the book example. So if you read the book, mine's different, but not by much. But let's get some more experience with this. I have to be able to do the Laplace transform of this. It's in the table. The Laplace transform of u sub a is in the table. But I just want to do the proof real quick because it's in the book, but it's worth looking at because it's kind of an easy proof. Think about it. I want to do the Laplace transform of u sub a of t. So it's the whole family of Heaviside functions. It's the integral from 0 to infinity of u sub a of t times e to the negative st. But u sub a of t is 0 until t equals little a. So I may as well integrate from little a to infinity. And when I'm at little a for t, that u sub a of t is now just a 1. I'm not even going to write that in. And this is a doable integral. All I need is a negative s right there and a negative 1 over s right there. That's all I need. I've got the chain rule adjustment ready to go. So this guy becomes the antiderivative is easy because I've got the chain rule. And now evaluate. When I put in infinity for t, remember t is the variable, put in infinity for t, I get e to the negative infinity. Doesn't matter what s is. I get e to the negative infinity. So that's 0. So I now put in the a. So I get negative, because I'm subtracting from 0, 0 minus negative 1 over s e to the negative as, because I'm putting in a for t. So this simplifies with two minus signs. It's just e to the negative as over s, which if you look here, that's what I've got. That's the Laplace transform of the Heaviside function. Piece of cake. So now let's solve this differential equation. We can now solve it using Laplace transforms because we can do the Laplace transform of each piece. So we're going to hit this thing with the Laplace transform. Yay! Now the Laplace transform of dy dt, we did it last time. I would have written it down, if it was me, I would have written it down in the table at the end of the book because you can use that anytime. So I have L of bracket y prime is s L of y minus the initial condition. So this side becomes s L of y minus 3, and that's equal to negative 2 L of y plus the Laplace transform of u sub a is e to the negative a. Well, in this case, it's a 4. So it's e to the negative 4s over s. So far, so good. Now, I'm going to bring the L of y stuff on one side, bring the 3 over. So I have s plus 2 times L bracket y equals 3 plus e to the negative 4s over s. I'm going to divide by s plus 2, and I'm going to have L bracket y, just like I always want. I want L bracket y equals 3 over s plus 2. That's not going to be a problem, child. And then plus the e to to the negative 4s over s times s plus 2. That's a problem, child, because I have e to the negative 4s over a product. The book table has a very complicated little piece of math, and this is the thing that you've got to grok for section 2 and for the rest of the chapter. Here's the big thing. It's right there, and it's kind of funny looking because it has the word easy in it. But what it's saying is the Laplace inverse transform of e to the negative as times somebody that is a Laplace transform, a known Laplace transform. So I'm just going to write on here, known. This big Y, I know where it came from. Well, that thing, if you do the inverse Laplace transform of this, it's the Heaviside function where the little a matches that little a. And then it's the little y that came with this big Y. So that's your function of t that generated this function of s. But it's not a function of t, it's a function of t minus a. So there's a little horizontal shift. The book makes a big fuss about the horizontal shift. I'd rather just do the formula. It's beautiful that in a page and a half you can explain where the horizontal shift comes from. It's beautiful, but you just got to be able to use the table. So let's check this out. I have to be able to see this guy as somebody's Laplace transform. Well, here's how to do it. It's 1 over s times s plus 2, and it's equal to a over s plus b over s plus 2. Now, believe it or not, I did the partial fractions on this. I'm going to save you the time. A comes out to be, the thing that's over the s comes out to be a half, I think. Let me make sure I got this right. It's crucial. It's on this side. Here we go. Yeah, the 1/2 goes with the plane s, and the negative 1/2 goes with the s plus 2. So now I can think of that function, 1 over s times s plus 2, is the same as 1/2 times 1 over s plus 1 over s plus 2 times negative 1/2. So leave those negative 1/2s and positive 1/2s out front. And now I can do the inverse Laplace transform. I'm going to save some writing by just erasing this top piece here. So I'm hoping you're taking notes as you go along. So now I'm going to hit this thing with the inverse Laplace transform. I think I'm ready. This thing becomes 1. L bracket y becomes y. That's the whole point of all this stuff. This guy becomes 3e to the negative st, or sorry, negative 2t. That's from this line here. When I have 1 over s plus 2, that's a being negative 2, so that's e to the negative 2t. Got it. And then 3 out front just because it's a 3 out front. Now this thing, if I use this formula here, this known y is the thing that would give me this piece here. That's my known y, big Y. It's known. What would give me that? It would be plus 1/2. Now I got to do 1 over s. 1 over s? Oh, it's this. It's this guy when n equals 0. So it's t to the 0. T to the 0 is a 1. Oh my God. All right. Minus 1/2 times this dude. Now that guy would be e to the negative 2t, but it's not. It's e to the negative 2 t minus a. My little a is a 4. So this is a t minus 4. T minus 4 up there. And all this is times u sub 4 of t, because it says I got to have a u sub 4 of t next to that little y, with every t replaced by t minus 4. I said a lot. You're probably going to watch this video a couple of times, especially after you go to try to do one step by step, because the book does a couple step by step. Here's one step by step with everything explained. This is the answer. That's your solution. Now, you can check it. You can actually check it. I'm going to just run through it real quick with you. When t is less than 4, this whole term is 0. So look at, when t is less than 4, it's just dy dt equals negative 2y. Oh, that's 3e to the negative 2t. That's an easy problem. And t equals 0 happens in that part. So look, when t equals 0, I get y equals 3. So this is satisfied. This is satisfied for t less than 4. Now for t bigger than 4, you change that to a 1. That u sub 4 of t becomes a 1. And now this is now t bigger than 4. And when you go to do this problem, to check it, you got to take its derivative, with that thing being a 1, and you're going to pop that in over here, and then do negative 2 times all this. Now negative 2 times all this is actually very friendly because you got these halves. And then plus, don't forget that's now a 1. And you do that. You make yourself do that because everything matches. The left-hand side and the right-hand side will be the same. So you've got something that satisfies the initial conditions, and it satisfies the differential equation in both time zones. And you can even graph this thing. You can even graph that if you want to. The book shows how. What should happen is you have the graph of 3e to the negative 2t, and then there's a cusp when this thing comes online. You get a new curve starting at that place, but the two pieces usually join. You don't usually get a jump. The two pieces usually join. So it's really funny. You have a discontinuous forcing term, but your solution is often continuous, which makes sense even for an explosion, because you have a situation and there's a sudden change in the situation, but even an explosion, it's still a continuous action. Just seems it's very quick, but it's a continuous action. So check it out. We'll be going further next time. Please do a few problems. Thank you.